Okay, welcome to Let's Get to the Marks, going through an ideal gas equation from the Paper 2 2023 Chemistry A-Level paper. A gas syringe that does not have any graduations is calibrated using a known mass of propanone, boiling point 56.2 degrees. The sealed gas syringe contains 0.146 grams of propanone, MR58, at a temp of 95 degree and a pressure of 103 kPa. Calculate the volume in centimeter cubed of propanone in the gas syringe. The gas constant is 8.31. Once again, I recommend when you're tackling papers, underline, highlight, and maybe even identify what you've underlined and highlighted, especially if it's a calculation question. Most important thing, of course, is to know what you're calculating. I've circled it here in blue. You're calculating volume. You'll be given R, 8.31. You'll be given temp and pressure, so you should all come to the same conclusion. You need PV equals nRT. Now, we want to find the volume, the V here. And you should recognize if we want to find V, we've got to rearrange. So I need to bring the pressure under nRT, divide both sides by pressure, and that will leave the V on its little lonesome over here. Okay, so we need nRT over P. So now all you have to do in these ideal gas equations is work out what's what, and make sure you do the conversions. So first of all, I want to work out the moles, which is N. And guess what? They're giving us mass and MR. I've just highlighted those there. And so you need to know this equation, most important one in chemistry, mass over MR times N. Easy peasy, lemon squeezy. 0.146 grams over 58. Now, what does that equal? Well, it equals 2.5 times 10 to the minus 3. It's actually 2.5 naught something or other. You should leave it all in your calculator in A-level chemistry. Let the scientific calculator do the work. I can't be bothered to write out really long numbers, so I'm going to round as I go, but bear that in mind, okay? The next thing we want to do is work out, we know that R is 8.31, so we really need to work out the temperature next. We don't have to work out R, it's already given to us. And the temperature for this equation, the ideal gas equation, is always in Kelvin. So add 273 to 95 and you'll get 368. Just a bit of mental maths. Now, the next part that we need to work out is the pressure. Now, the pressure is 103 kPa. And what you do have to know is that pressure needs to be converted into pascals. So you need to times that by 1,000 and you'll get 103,000 pascals. You need to know about these conversions for the ideal gas equations. And then this is easy, easy, easy marks. But you have to, for A-level chemistry, know when you get to ideal gas, you're going to need conversions. Okay, so now let's plug all the figures in. So we want 2.5 times 10 to the minus 3 or whatever it is in your scientific calculator times 8.31 times 368. Oops, I typed the wrong thing there. Let me just change that. So that should be 368, not 2.5 times 10 to the minus 3. I'll just go back and change that. We're going to divide that by the pressure of 103,000. And remember, that's going to give us our volume in meters cubed, okay? So let me just change that because I made a bit of a mess up there by putting 2.5 times 10 to the minus 3 twice. That should be 368 there. Whack that in the calculator and you should get 7.4 times 10 to the minus 5. They're all thereabouts, and that's going to score you another mark for that. Now, that's not really our final answer, so that's our third mark. Where's the fourth mark come from? Well, this is in meters cubed, and of course, they want the answer in centimeter cubed. To turn meter cubed into centimeter cubed, we times by 1 times 10 to the 6 or by a million. Now you might say, why by a million? There's only 100 centimeters in a meter. Well, it's a cube, so 100 by volume 100 by 100 by 100 to the power of 3. So that's where you get it from. That's where you get the milli from. Okay, now in my calculator it came out as 74.2, but I'm putting 74 centimeters. If you use the rounded numbers throughout, if you don't, you get slightly higher. Now there'll be some leeway in the mark scheme for that. All right, let's zing, 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 zing down to the next question. Okay, 7.2. The gas syringe then cooled to 75 degrees without changing the pressure. Calculate the decrease in volume if you were unable to calculate the volume in question 7.1, you should use the volume 89 centimeter cubed. That is not the correct answer. So we know that the temperature went from went from 95 to 75. So that's 368 to 348. And all we need to do is plug all these numbers back in the calculation and rework it out. So 2.5 times 10 to the minus 3 times 8.31 times 348K. We got the 348K because we did 95 from the original question, take away 75, which the temperature was lowered to, divided by 103,000. It told us the pressure was the same, 103,000. And we're going to get, bada bada bing, bada bam, bada bong, we're going to get 7 times 10 to the minus 5. They're all thereabouts, 70169 or whatever. But 7 times 10 to the minus 5. Now, once again, I need to times by 1 times 10 to the 6, not 1 times 10 to the minus 6. Oops. I nearly wrote, 1 times, not minus 6, 1 times 10 to the 6. And that's going to give us like 70 centimeter cubed. But of course, I nearly wrote that answer in. That's not your final answer. That's only 1 mark, all that work. It said the decrease in volume, which I've just circled here. So 74 from the original volume in the original question minus 70 times 70 centimeter cubed equals 4 centimeter cubed. Now, there we go. Let's move on. About time. Keep moving on, keep moving on, keep moving on, keep moving on. 7.3, we've been given the total uncertainty, which is plus or minus 0.001. And that's the uncertainty in the balance we used to measure the mass in the first question. It now says what will be the uncertainty in the volume. Well, we need to start off with our uncertainty in the mass. And how you do that is you do the uncertainty over the mass, over your measurement. So 0.001 divided by 0.146 times 100, we're going to get 0.685. Now, that's a percent. Don't think that means 68%. Okay, so that scores us 1 mark. But we've got another bit to this, which is probably the bit that some people might mess up on. So our original volume was 74 centimeter cubed from 7.1 from the first question. That's the volume we calculated. Of course, you can use 89 centimeter cubed if you messed it up. So now we want to work out what the uncertainty is in that. So this 74 centimeters is possibly going to be 0.685 out, is how much it's going to be out as a percentage. So what I need to do is 0.685 divided by 100 times 74 centimeters, because and that will get you the correct answer. Remember, when you times by a percentage, you need to turn it into a decimal of that percentage. So you've got to divide by 100. So you just got to remember to divide the 0.685 by 100. Otherwise, you're doing 68.5% times the volume. And so it's like 0.51, but I'd probably call it 0.5 is a better answer to put down for the centimeter cubed uncertainty. And that's the end of 7.3. Let's zing on to 7.4. We're getting there, folks. Just last part to this question. Let's go. 600 centimeter cubed of propanone is mixed with 2,800 of oxygen in a container at 60 degrees and 100 kilopascals. The mixture is ignited. When the reaction is complete, the remaining mixture of gases is cooled back to 60 degrees at the same pressure of 100 kilopascals. And we have an equation here, which means we're going to use coefficients. So we got 600 centimeter cubes of propanone, and we got 2,800 centimeter cubed of oxygen. We don't know which one's in excess yet. The pressure's the same before and after. Now that's interesting, because if the pressure is the same, we could just, it means our centimeters are like equivalent to moles, basically. So what we're going to do here is we're going to use the ratio of the coefficients. So propanone to oxygen is 1:4. So for 600 centimeters of propanone, I'm going to need 2,400 centimeter cubed of oxygen, right? So it means I'm going to need 2,400 centimeter cubed of oxygen to react with that 600 centimeter cubed of propanone. So the leftover oxygen is going to be 2,800 minus 2,400 centimeter cubed. which is the amount of oxygen that reacts fully with the propanone and uses all the 600 propanone up. And it means I'm left with 400 centimeter cubed of oxygen left over. And that's a gas. So that's going to be part of our remaining mixture of gases that they're asking us to find the volume for. We don't need to take account of the water because that's a liquid, so it's not relevant. It's not going to be part of the volume of the gases, but we do need to work out how much CO2 is produced. Now, because we've got 600 propanone and the ratio of propanone to CO2 is 1 to 3, we're going to times the propanone by 3 to get 1,800 centimeter cubed of carbon dioxide. Remember, the propanone is the limiting factor here, so that's the max CO2 we can make. We need to whack the leftover oxygen and propanone together, 400 plus 1,800, and that means we've got 2,200 centimeter cubed in our mixture of gases left over. Nice. All right, guys, remember to hit the like, share, subscribe, punch up the bell. Let's get to the marks.
You're still here? It's over.